Good evening, everybody, and welcome to another online session of organic chemistry. For today's session, we are going to focus on the chemistry of carboxylic acid and nitriles. And for that, we are going to use the end of chapter 20 problems in R. So we do have a lot of material to cover today. So to get the session started, let's see who is here. Lisa, go ahead and read this question for us.
Give the IUPAC name, including any stereochemistry for the following carboxylic acid.
Okay, very good. I see that Kia has joined us. Oh, Kia, you are welcome. Okay, what they want us to do here is to give the IUPAC name for this molecule here. As you can see, in this molecule, you have a carboxy group. This is your hydroxy group, and this is your carbonyl, so this is a carboxy group. And you also have a carbon-carbon double bond. If we take a look at this molecule here, what would be the longest carbon chain that contains the carboxy group if we have to give the IUPAC name? Does anybody have an idea? The longest carbon chain that contains the carboxy group. How many carbon atoms? Pentane, great. Okay, so this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, and carbon number 5, which means that this methyl here will be a substituent, and also that also means that this propyl group right here will also be a substituent. Okay, so let us go to my notebook so we could do this problem together. I also noticed that a lot of people have joined us. Brea, you are welcome. Dimitris, you are welcome. Let's see who else is here. Robert is here. Shiranda is here. You are all welcome. Okay, so let us go. Let me go to my notebook so we could start doing this problem. Okay. This is the problem that we have right here. This here, right here. So what I want to do, let me draw the two-dimensional structure before we start solving giving the IUPAC name. So we start with the carbon-carbon double bond. And there is a methyl here. Another methyl here. And then we have here a CH attached to a carboxy group. And then here we have a CH2 attached to that. And then attached to that is another CH2. And then attached to that is a CH3. Now, if you see the structure that I have drawn here, give me a happy face. Okay, if you see this structure here, give me a happy face. Okay, let's see here. Okay, I see a bunch of happy faces. Very good. So that means that you all see this. Good. So now, we say that the longest carbon chain contains the carbon-carbon double bond, which is this one here. So this is carbon number 1. Now let me change my pen. Carbon number 1, carbon number 2, number 3, number 4, and carbon number 5. So what would be the IUPAC name for this molecule? What would be the IUPAC name for this molecule? Well, let me ask you another. Maybe I should ask you a more specific question. What would be the base name for this molecule? What would be the base name for this molecule? We know we have the longest carbon chain is 5. Okay, pentanoic acid. Excellent. Pentanoic acid. Very good. Okay, pentanoic acid. So that would be the base name. So we have pentanoic acid, pentanoic acid, because we have the longest carbon chain is 5. Now, where is the position of the double bond? Where is the position of the double bond? Okay, 3. So we have to say 3 pentanoic. Okay. About all of the other substituents. Okay, we need to complete this name. What other substituents do we have here? We have this here. We have this propyl group. We also have this methyl group. Okay, keep in mind you have to name this in alphabetical order. Excellent. Excellent. Okay, Blair said 4-methyl-2-propyl. Same thing with Sinead. Okay, that is great. Okay, so let us complete this name. So that becomes 4-methyl, then 2-propyl. Take these 3 out of the way. Pentane. Okay, so that is the name of this molecule. If everybody see this as being the name, give me a happy face. Or if you have a question, give me a red X. Okay. No red X's. So everybody agree with this name? Okay, very good. So now let us go to other nomenclature problem. Okay, Mela, go ahead and read this question for us. Okay. Julian, go ahead and read the question for us.
Give IUPAC names for the following compounds.
Okay, good. Give IUPAC name for the following compounds. So let us try A first. Okay, if you take a look at this molecule, let us number the carbon chain. 1, 2, 3, 4, 5. Okay, so what will be the name of this molecule? We have substituents in position number 4 and position number 5. What will be the name? 4,5-dibromopentanoic acid. Excellent. Okay, that's Dylan. Okay, very good. 4,5-dibromo, because we have bromine in position 4 and 5, pentanoic acid. Okay, very good. Okay, I see Melat has joined us again. She must be having problem with her internet. Okay, let us try this. What will be the base name for this molecule here? For B, the base name for this molecule. What is the longest carbon chain? Containing the carboxyl propanoic. Okay, excellent. So this is carbon number 1, carbon number 2, carbon number 3. Okay, so what will be the name of this molecule? 2,2-dimethylpropanoic acid. Excellent, that's clear. Okay, very good. 2,2-dimethylpropanoic acid. See, I see that you guys do not have any problem with nomenclature. That is good. Okay. Okay, now let us name this here. Let's see. Dylan, go ahead and read this for us.
Draw the structure of 2-cyclobutene carbonitrile in the window below.
Okay, 2-cyclobutene carbonitrile. So what will be the base name for this molecule? What will be the base name for this molecule? We have 2-cyclobutene. How many carbon atoms do we have in there? In the base name? Butene. Okay, we also say cyclo. So this will be exactly. So this will have to be cyclobutene, 4 carbon atoms. Okay, we say carbonitrile means we have a carbon-carbon triple bond, which is a nitrile. And then we say 2. Keep in mind, this is position number 1 right here. And therefore, this is position number 2. So this becomes a double bond is here. So therefore, this becomes 2-cyclobutene carbonitrile. Okay, very good. Okay, so we are moving right along. Go to here. Okay, Amelat, if you are back, can you read it for us? Okay.
Okay. Can you hear me?
Yes, go ahead.
Alpha ketoglutaric acid is an intermediate in the citric acid cycle of carbohydrate metabolism. It has the systematic name of 2-oxo-pentane iodic acid. Draw the structure of alpha ketoglutaric acid.
Okay, this will be this is something new to you guys. Now, what you have here are very good, by the way. I noticed that you have problem with your internet, Melat, so I'm glad that you are back. Okay, so you have this molecule here, 2-oxo-pentane dioic acid. Okay, so we take a look at the pentane dioic acid, which means that we have 5 carbon atoms. The longest carbon chain contains 5 carbon atoms. So we start with this. Dioic acid means that we have 2 carboxyl groups, di, and it says pentane dioic acid, so 5 carbon atoms. So far I have 4. I draw 1 more. Now, anytime you see the word, the prefix, anytime you see the prefix oxo, this means carbonyl, same as carbonyl. Okay? So whenever a carbonyl is a substituent, we use the prefix oxo. Just as when you have a methyl group, we say when you have a CH3, we call this methyl group, right? So whenever we want to use a carbonyl as a substituent, we refer to it as oxo. So therefore, if we say we have 2-oxo-pentane dioic acid, what do you think that molecule would look like? This is the base name right here. Anybody has an idea what the molecule would look like? We have 2-oxo-pentane dioic acid. Anybody has an idea? pick up the mic, or you could send me the suggestion through the chat window. The carbonyl will go on the second carbon. Excellent. Oh, Eric, by the way, you are welcome. Oh, Eric has told us that the carbonyl will go on the second carbon. So therefore, we have to say that the carbonyl is right here. So let me write that better. The carbonyl will be right here. Okay, so therefore this becomes 2-oxo-pentane dioic acid Okay, is that clear? If it is clear to you, give me a happy face. Okay, supposing I have this molecule. Supposing I have this molecule. Let us use another molecule. Supposing I have this. Okay, how will you name this molecule if I want to name this as an aldehyde? How will you name this molecule if I want to name this as an aldehyde? Given what I just told you here, how will you name it? Okay, let us count 4-oxo-hexanal. Okay, let us see, is that correct? Dylan said 4-oxo-hexanal. This is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6. So Dylan is correct. That is correct. So that becomes 4-oxo. Okay, Blair, you are also correct. 4-oxo-hexanal. Now, okay, very good. Okay, so let us move to the next one. Okay, how about this one here? Kia, is your mic working? If your mic is working, can you read it for us?
Identify the most and the least acidic compound in each of the following sets.
Okay, very good. Identify the most and the least acidic compound in each of the following sets of molecules. Okay, so let us try A first. Now, before we do that, let me give you a little bit of background information. Anytime you are referring to acidity, that a molecule is acidic, according to Bronsted acid-base definition, Bronsted acid-base definition. Okay, this is D. Now, if you are taking a look at a molecule and you say the molecule is acidic, now basically what you are saying is that the conjugate base, that is after you remove the proton from the molecule, the conjugate base is very stable. Say for example, let us take a look at this molecule here, 2,4-dinitrobenzoic acid. Let us take a look at it. We have benzoic acid. Say 2,4-dinitro. We have a nitro group here. We have another nitro group here. That is 2,4-dinitrobenzoic acid. Now, when we say this molecule is acidic, we are essentially saying that this molecule will be willing to give away this proton right here. to become a conjugate base. Okay, let's just imagine that we have lost the proton. Okay, now once we do that, we have the nitro group here. We have another nitro group here. Now the strength of any acid, based on Bronsted acid definition, the strength of any acid, let me write this down, the strength of any acid, because this is very important, the strength of any acid depends on the stability of its conjugate base, In this case, for this molecule, this is the conjugate base right here. The conjugate base is that species that you obtain after you lose the proton. Okay, now, in order for this molecule, this conjugate base to be stable, if you keep in mind we have electrons here. So anything within the rest of the molecule that is capable of drawing electron away from here will make this conjugate base very stable. Now we all know that the nitro group is electron withdrawing. So here we have two electron withdrawing groups on the benzene ring. So the net effect is they will be pulling electron away into the ring system, thereby stabilizing this ion right here. Okay, so that is the basis for anything that we do when we say a molecule is acidic or not acidic. In other words, the question you need to ask yourself is the conjugate base stable? Okay, so now let us, given that information, let us see whether we can now answer this question. Okay, I am going to erase this. The first set of molecules they have given us, this here, we have 2,4-dinitrobenzoic acid, which is this molecule here. Then you have p-nitrobenzoic acid. So let me write that, p-nitrobenzoic acid. P, that is para, is in this position here. Then we have p-bromobenzoic acid. Now, of all these molecules here, we know that bromine is the least electron withdrawing atom, substituent within these molecules that we have here. The nitro group is strongly electron withdrawing. The bromine is mildly electron withdrawing, not as much as the nitro. So given that information, which of these three here will be the most acidic? Let us call this number 1, number 2, number 3. Which is the most acidic? Which is the most acidic? We want the most exactly. Number 1 will be the most acidic. Very good. Why will it be the most acidic? Why will it be the most acidic? Anybody has an idea? Electron withdrawing groups. Okay, because the conjugate base will be stabilized by 2 electron withdrawing groups on the benzene ring. Excellent, excellent. Now, which will be the least acidic? That is the question they are asking us. Which will be the least acidic? Number 3. Excellent. That is correct. So this is the least, and this is the most. Okay, very good, very good. So now let us go to the next one. Okay, so we are now going to use the same rationale for B, for this one here. So we are going to use the same rationale for that. We have oxalic acid. I know you guys do not know the structure of oxalic acid, so let me give that to you. This here. That is oxalic acid. And then you have acetic acid. And finally you have formic acid. This is acetic acid. This is oxalic acid. And this is formic acid. Okay. Given the information that you know so far, which will be the most acidic of these 3? Which will be the most acidic? Let us call this 1, 2, and 3. Which will be the most acidic? 1. Very good. That is correct. Why would it be the most acidic? That is correct. But why will it be the most acidic? Most acidic. Okay, the conjugate base will be stabilized by electron withdrawing group, because if you remove this hydrogen here, you form a conjugate base right here, and that will be stabilized by what we call inductive effect, because we add this carbonyl here will be drawing electron away from this here. So it will be stabilized by inductive effect. Inductive effect simply means pulling electron away from one part of the molecule to another part of the molecule. Okay, very good. So which will be the least acidic? Which will be this? Okay, by B, are you referring to 2? When you say B, are you saying 2? Yes, okay, very good, very good. Because of the methyl group, excellent. So this will be the least acidic. Because here, the methyl group, and generally alkyl groups, they have a tendency to donate electron or to direct electron to another carbon atom. So because the carbon is, in this case, this carbon is attached to 3 hydrogen atoms. It will be pulling electron away from hydrogen, and of course destabilizing the conjugate base, which will be here. So because of this alkyl group, specifically because of this methyl group, that will stabilize destabilize the conjugate base. So therefore, this will be the least acidic. In this case, you do not have a methyl group. You simply have an hydrogen attached to this carbon. The hydrogen doesn't pump electron to the system as much as the methyl group will do. So therefore, this is the least acidic. Okay, now let us go to this one here. Okay, here we have cyanobenzoic acid, right here. Cyanobenzoic acid. We have benzoic acid. P-cyano, cyano is here, which is a carbon-nitrogen triple bond. And then you have benzoic acid. Mellard is having problem tonight with her internet. She keeps going in and out. Okay. That is benzoic acid. And then we have aminobenzoic acid, P-aminobenzoic acid. P-amino. Okay. Which will be the most acidic of these three? Let us call this 1, 2, and 3. Which will be the most acidic? Which will be the most acidic? 1, 2, or 3? Okay. Okay, keep in mind, the cyano group is very electron withdrawing. The cyano group is very electron withdrawing. On the other hand, the amino group is electron donating. If you remember when we did aromatic chemistry, the amino is electron donating, the cyano is strongly electron withdrawing. So, which will be, okay, great, BR said 1. Okay, so this will be the most acidic. Which will be the least acidic? Okay, least acidic, number 3, least. Okay, very good. That will be the least acidic. Okay, so if you get this kind of question in any quiz or exam, this is the same kind of rationale that you have to use. This is all based on the stability of the conjugate base. Any atom or group that will stabilize the conjugate base will make the conjugate base very stable. Say for example, let me ask you this. Supposing I have this, I think we did this in class. Supposing I have this here, this molecule here, chlorine here, and this molecule here. Now, which of these two molecules will be the more acidic? Let us call this 1, and this is 2. Which will be the more acidic? Which of these two will be the more acidic? Okay, the more acidic will be exactly 2, because once you form the conjugate base right here, because of the proximity of the chlorine atom to that conjugate base right here, it will have a greater opportunity to pull the electron away to itself. So therefore, this will be the more acidic. Very good. Okay. Okay, so now let us go to the next problem. Okay, now let us begin to now look at reactions. Okay, let's see. Who do I need to call on here that I've... Jamie, is your mic working? If your mic is working, Can you read this for us? Okay. Oh, it doesn't work. Your mic is not working. Okay, I got you. Okay, let's see. Sharanda, is your mic working? If it is working, can you read this for us? Oh, no, it doesn't work. Okay, let me go to, I know, listen, I know your mic is working. Go ahead and read this for us.
How could you synthesize the following compounds from butanoic acid using reagents from the table?
Okay, what I want to do, I don't want you guys to see this. So let us take this out of here. I'm messing up my paper here. Messing up my ink also. I see Shine is smiling right now, or laughing at me. I knew you were laughing at me. You see, I know you by now. Okay. Okay. How will you synthesize the following compounds from butanoic acid using reagents from the table below? Forget the reagents from the table below. You have to make this. We also have to make this. Okay, so let us start. They want us to make, starting from butanoic acid, they want us to make 1-bromobutane. 1-bromobutane. Okay, so how do we do that? What is the first thing that you're going to do? Okay, if you look at this molecule here, let's do some analysis here. We have 4 carbon, how many carbon atoms here? 4. We have 4 carbon atoms here. So there is no new carbon-carbon bond. All we have to do is change the functional groups. Okay. How do you go from a carboxylic acid to an alkyl bromide? What is the first step? Okay, what is the first step you want to go to take? We want to go from this carboxylic acid to this alkyl bromide, turn carboxylic acid into an alcohol, then alcohol into bromine. Excellent. I like that. Okay, that's brilliant. Okay, very good. Okay, now how do we turn a carboxylic acid into an alcohol? What reagent do we need? Okay, that is an excellent analysis right there. So what reagent do we need? Now don't look at here now. What reagent do we need to turn to an alcohol? Okay, lithium aluminum hydride, step 1. Very good. Lithium aluminum hydride followed by hydronium ion, and that will give us the primary alcohol. I see Lauren has joined us. Lauren, you are welcome. I'm sorry, let me take this. Okay, then how do we then go from this alcohol to the alkyl bromide? What reagent do we need? What reagent? Oh, PbR3X, phosphorus tribromide. Okay. See, I know that you guys do not need this table here. Okay, PbR3. Okay, so that problem is solved. Now the next thing they want us to do now is to now take the same butanoic acid. They want us to convert that same molecule to octane. To octane, that is 8 carbon atoms. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that is what they want us to do. I'm going to give you some help here, because I don't think we have done this type of reaction before. Now, once you form this, keep in mind at this point, what this is telling you that we need to form new carbon-carbon bond. Indeed, we have to double the carbon chain, because we are going from 4 carbon here to 8 carbon. So this is what you do. Okay? Fortunately, we have shown you how to make the alkyl bromide. In this case, if you take the copper lithium reagent, and you react with a primary alkyl halide, you get an SN2 reaction. That will displace the bromine. Okay, so having given you that information, okay, so let me take this out of here. Okay, so the first thing I want to do now is to make the copper lithium reagent. We have step 1. You add lithium with the alkyl bromide will form butyllithium. So let me just take the one out of the place. Let's go step by step. You add lithium to that. You form butyllithium. Remember how we make the copper lithium reagent. So you form butyllithium. Then, to make the copper lithium reagent, then you add 2 copper iodide to that. And when you do that, you form your copper lithium reagent. Now you have CH2, 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 2 of them here. Then you have copper. Then you have lithium. So now you form your copper lithium reagent. Now if you now take that, and now you add that, do an SN2 reaction with the copper lithium reagent, with this alkyl bromide that you made, that gives you your product. That gives you your product, okay? So keep in mind, like I said, this is the first time we are doing this. Copper lithium reagent or Gilman reagent, if you recall the name. Who undergo an SN2 reaction with a primary alkyl bromide or alkyl chloride to give you an alkane. Okay, or the corresponding compound in which you have formed a new carbon-carbon bond. Okay, now let me erase it to see what we have here. Okay, do we see what we need? Okay, we say for this part here, what do we have? Okay, so we form our copper lithium. Okay, of course we have butane, which we made already right here. Lithium reacts with that to form the lithium butyllithium. Then we add 2 moles of copper iodide, and that is what you have here. Now you have your copper lithium reagent, and now then you dump in your another 1 bromobutane. Of course, we made the bromobutane already, so that is fine, and that is how you get this here. Okay, if that is clear to you, give me a happy face. Okay. Okay, I see Snare, Melat. Okay, I see Dylan, Melat. Okay. Okay, very good. Eric. Okay, let me see. I need to. How many of you have not talked to yet? Robert, is your mic working? If your mic is working, can you read this for us?
How would you convert the following compounds into butanoic acid using reagents from the table?
Okay. Once again, we do not want to look at the reagent, so let's just simply take this reagent out of the way. Okay, how will you make this compound here from what we have here? How will you convert the following compound into butanoic acid? Okay, so what do they want us to do? They want us to take 1 bromobutane and make butanoic acid out of it. That should be very simple. That should be very, very simple. Butanoic acid. Okay, so how do we do that? 1 bromobutane. Can anybody give us a sequence of reactions? 1 bromobutane to butanoic acid. 1 bromobutane, of course, will be this molecule here. Okay, so how do we do that? Any idea? 1 bromobutane. We have 4 carbon here. We are ending up with 4 carbon right here. So how do we do that? Any idea? Keep in mind, since we have 4 carbon here, we also have 4 carbon here. We are not forming a new carbon-carbon bond. All we are doing at this point is functional group transformation. Functional group transformation. Any idea? Okay, let me see if I can help you out here. Okay. Do you know of any method that you can use to make this carboxylic acid? Supposing just start with, you could start with any starting material. How will you make this? Start with any starting material. Chromic anhydride. Excellent. Chromic anhydride with what? That is good. That is good. Chromic anhydride with what? Okay, with what? Okay, well, we could do that. I will do butanol. Okay, so you want us to make with this here. Okay, now keep in mind now, that is actually this problem. So what you have done now, you have solved the second problem for us, because they also want us to make it from butanol. Now the next question is, how do we make it from 1-bromobutane? Okay, so this problem is solved. That was Brea. Brea has solved this problem for us, butanol to, because this is butanol to butanoic acid. Okay. Can we oxidize a primary alcohol to carboxylic acid? Yes or no? Can we oxidize a alcohol? Yes. Okay, if we can do that, then why don't we say that if that is possible, that we could simply take this here. If we say we want to oxidize a primary alcohol, so we want to turn this into a primary alcohol. No, lithium aluminum hydride will not do that. So it will be hydroxide. If you remember last semester, okay, we can do an SN2 reaction using an hydroxide on this primary alkyl bromide, and that will give you a primary alcohol. Okay, SN2 reaction of an hydroxide on a primary alkyl halide will give you a primary alcohol. Okay, so this is the first part. Now, the next thing you now do, we now use the reagent that Brea gave us earlier, which is chromium trioxide. Chromium trioxide in some acid, and that will give you that. So the answer to this is you go from the alkyl bromide, you form the primary alcohol by SN2 displacement using hydroxide, and then once you form the primary alcohol, you oxidize the primary alcohol to a carboxylic acid using chromium trioxide. Okay, very good. Okay, so we have solved that. The second part here, we solved that already. Brea gave us the answer to that. So this here, simply take okay, what you simply have to do here is simply take this butanol, chromium trioxide in acid. Okay, that takes care of that. Okay, let us see here. Okay, now let us try this. Okay, who do I need to? Lorraine, is your mic working? If your mic is working,
how would you synthesize
can you read this question for us?
From butanitrile using reagents from the table?
Okay. So we want to synthesize this compound, this here, butylamine and 3-hexanol, starting from butane nitride. In other words, let us do A first. A, butane nitride, so that would be this here. This is butane nitride, and they want us to make this here butylamine. They want us to make butylamine. That should be fairly simple. Okay, that's butylamine. Okay, what reagent do we need? That should be very, very simple. Okay, there is no new carbon-carbon bond. all we are doing here is transforming the nitrile to the primary amine. So this is another case of functional group transformation. Excellent. Okay, Kia said lithium aluminum hydride, and also Sinead said lithium aluminum hydride. That is correct. So the answer here is 1, lithium aluminum hydride, and then step 2, hydronium ion. Okay, keep in mind this reagent here will transform a nitrile into a primary amine. This is a primary amine. Okay, I believe in chapter 24 or 23 we are going to study the chemistry of amines. Okay, so we've done A. About this one here, now they want us to go from the same butane nitrile as above, now they want us to make 3-hexanol. 3-hexanol. Yeah, they want us to make an alcohol. 3-hexanol. That is 3-hexanol. They want us to make this from here. Okay, how will you do this? Okay, before you do this, do some analysis here. Here we have a molecule that has 4 carbon atoms, and here they want us to make a molecule that has 6 carbon atoms. So how many carbon atoms do we need to add to this molecule? How many? 2. Okay, very good. So now you know we need to add 2 carbon atoms. Now do not look at here now. I don't want you to look at here. Okay, so what do we do here? What do we do? We want to extend the carbon chain. Okay, somebody. Okay, very good. Excellent. Okay, so now you're going to use a Grignard. Okay, so Eric wants us to use a Grignard. Very good. You use ethyl magnesium bromide. That is our Grignard that Eric wants us to use. Very good. So we do that, and then of course step 1, step 2, and that will give you what would this give us? What would this give us? What will it give us? A Grignard reacting with a nitrile. What will it give us? That is the right step, but what would a ketone? Excellent, will give us a ketone. So we have change the color here. That is coming from the Grignard, and then the blue is coming from the nitrile. Okay, so now we get this ketone. Keep in mind, this is where we want to go. So then, how do we get here? How do we go from here to here? We have our ketone here. Okay, lithium aluminum hydride. Okay, very good. What other reagent can we use? Is there any other reagent you could use? Sodium borohydride. Okay, we could use sodium borohydride. So since we have not used this in a while, so we do not forget this, so let us use this here. Sodium borohydride, followed by hydronium ion. Okay, that would take a ketone to a secondary alcohol, to take a ketone to a secondary alcohol. You could also use lithium aluminum hydride followed by hydronium ion. That will also take a ketone and transform a ketone to a secondary alcohol. Okay, so we've done both of those. Okay, now what does this one say? How will you synthesize? Okay. Oh, okay, I don't think I have this. Well, okay, I don't have this molecule here, so that's my error here. So let's go to 12. Okay, this should be a good one. Okay, let us see. Julianne, go ahead and read this question first.
Select the starting material and a series of reagents necessary to synthesize the compound in as few steps as possible.
Okay, so they want us to synthesize this molecule here in as few steps as possible. Okay, I'm going to tell you now. Supposing I want you to start from now, let us say we start from, where do we want to start from? Because they did not tell us where to start from. Really? Okay, so I would say start from here. Okay, starting from here, how will you make this? How will you make that? Of course, this one is right here. Okay, let us assume we start from there. How will you make this compound here? Okay, you want to form a Grignard first? Okay, good. We form a Grignard. Okay, so let us start with that. We make a Grignard reagent. Okay, now what do we do next? Okay, so that would be this carbon here and this carbon. Now we need to, okay, carbon dioxide. Which type of carbon dioxide do we want to use? Carbon 13 dioxide. Okay, very good. Because at this point we need to introduce carbon 13 right here. So that means we take step 1, we take carbon 13, carbon dioxide, and then step 2, hydronium ion, and that will give us this here. Let us place our carbon 13 here. Okay, so this is our carbon 13 carbon right here. So now what do we do? Keep in mind, this is where we're going. So far, we have introduced this carbon, and this carbon. So we have one more carbon to go. What do we do? Okay, what do we do? What do we do? We have one more carbon to go. So what do you want us to do at this point? Okay, you could go ahead and look at here. Look at here. What do we do? What's the agent do we need? We've formed 3 carbons. We need one more carbon to go, this here. Okay? Any idea? You need more than one step. You need more than one step. Okay, you want to reduce the carboxy group. Very good. That's Eric. Good. Eric said we should go ahead and reduce the carboxy group with lithium, aluminum hydride, followed by hydronium ion. So that gives us, that will give us this here. This here, let me change my color to show the carbon 13 right there, it's still there. So that gives you a primary alcohol. So what do we do with that? PbR3. Okay, good. Now we do PbR3. If you do PbR3, you now have CH3, CH2, and carbon 13 is here. And now we have bromine. So now what do we do? Okay, now you do magnesium, green here. Okay. So let us now do step 1, magnesium. Step 2, carbon dioxide. Step 3, hydronium ion. And that will give us the product that they want. That will give us the product that they want. CH3, CH2, CH2, and of course okay. Now if you guys follow that synthetic scheme that we are just giving you, give me a happy face or a green check. Okay, happy faces. Okay, very good. Lots of happy faces. Good, good. Okay, so now let us see. 13. What time is it? Okay, we do a couple more problems before we leave. It's about 8:07 now. Okay, let us see this problem here. Okay, this is a good one. Let's try this. Okay, who do I need to talk to here? Somebody who has not talked to me yet. Okay, let's see. Okay, Dimitris, is your mic working? If your mic is working,
select reagents on the
read it
table
for
to
us.
show how you would carry out the transformation. If more than one route exists, use one that requires a few steps.
Okay. Now that was what they want us to do here. I see Jessica Williams is joining us. You are welcome. Okay, what they want us to do here is to select the most efficient route or scheme for this transformation, going from here to here. Okay, let's take this out. I don't want to look at this. Okay, so what do we do? Let us do some analysis here. We have 1, 2, 3, and 4. 4 carbons. 1, 2, 3, and 4. So this carboxylic carbon here, we have to add this carbon. This is a new carbon. Essentially means that we have to add that to this position right here. Okay? So what do we do? Okay, anybody has an idea? Somehow we need to functionalize this carbon here and then make a new carbon-carbon bond to this carbon. Any suggestion? Okay, the first thing you functionalize that carbon. Functionalize for those. Okay, you functionalize this carbon. In other words, by saying functionalize, give it some kind of living group or some kind of, add some atom to it that is not hydrogen or carbon at this point. Okay, so what do we do? Keep in mind we need to form a new carbon-carbon bond. Okay, let me give you a hint. MBS, excellent. Okay, so Bria has saved the day. Brominate, okay, Eric said brominate, also great. Okay, MBS is the best reagent for this. Anytime you have a carbon-carbon double bond, if you have an allylic hydrogen, this here, here you have allylic hydrogen here. Actually, you have two of them. Okay, anytime you have allylic hydrogen, okay, allylic hydrogen is that hydrogen that is attached to allylic carbon. Of course, allylic carbon is that carbon that is attached to a carbon-carbon double bond. Okay, so anytime you have allylic hydrogen, you could replace any one of those hydrogen by using MBS. That is an excellent reagent. So, therefore, let us do that. So we take this here, NBS. So that will give us bromine. Yeah, that is what MBS will do for you. So we form that. Keep in mind, this is where we want to go. So now what do we do now? Now that we have functionalized this carbon here by bromination, so what do we do? Oh, okay, Grignard. Okay, we go back to our Grignard. Okay, very good. So we now add Grignard. Step 1. Let us save ourselves some time here. What is step 2? Carbon dioxide. Very good. What is step 3? Hydronium ion. Okay, you guys solved that problem. Very good. I really did not have to do too much work tonight. And that would therefore give us this product right here. Okay, is there any other way you could do this? Is there any other way you could do this? Any other way you could do this? Any other way to do this? Okay, this is a good one that you've just given us. Is there any other way? Okay, let us assume that we make this here, from this allylic bromide here. Can we use any other route, any other scheme? And what would that be? Okay, assuming that we've made this here, we made this molecule. Okay, yes, cyanide, SN2 reaction, exactly. We could do an SN2 reaction. We could do an SN2 reaction. So if we take sodium cyanide, okay, and we do an SN2 reaction on this secondary allylic bromide, and that will give you this here. The cyanide, and then you have that will give you that. Then you now take that. How do you go from the cyanide to the carboxylic acid? Hydronium ion, excellent. Okay, so addition of a reaction of cyanide in an SN2 reaction is another way of making a new carbon-carbon bond. Okay, in this case, we get rid of the nitrogen by simply hydrolyzing the cyanide group with hydronium ion to form the carboxylic acid. Okay, very good. Let us, I think we're moving right along. Let's see. Okay. It's a good one before we leave. Okay. Jessica, is your mic working? If your mic
Select
is working, can
reagents
you
from
read
the
it
table
first?
to carry out this transformation.
Okay. So what they want us to do here, use reagents from here to show how to go from here to here. Okay. Now, what do you think we need to do? What kind of analysis do we need to make here? Let's look at the starting material. How many carbons do we have in the starting material? How many? How many carbon in the starting material? 4. Okay, good. So we have 4. 1, 2, 3, and 4. How many carbon do we have in the product? This is 1, 6. Okay, we have 6. So we want to go from here to here. So therefore, we definitely need to make new carbon-carbon bonds. And at the same time, we are supposed to make primary amine. Indeed, 2 primary amine. Okay? So the 2 questions I have for you: how many extra carbons do we need to add to the starting material to get to the product? How many extra carbons? 2. Okay? So that is good. Then we also need to make 2 amino groups, 2 primary amines. How do you make primary amines? How do you make, okay, cyanide, okay, so we have solved our problem. You form cyanide, okay? So if we can form cyanide, and then we reduce the cyanide, okay, so therefore, let us go one step at a time. So, according to what you guys are telling me, if we have this, we have amino on this side, amino on this side, so this carbon could come from the carbon of the cyanide, this carbon could come from the carbon of the cyanide, okay? If that is the case, then what do we have? We have, okay, let us see here. So we have, let us see, carbon, cyanide on that side, CH2, 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 those are the original carbons. Then this carbon from cyanide. So what reagent do we need here? What reagent do we need here? Lithium aluminum hydride. Lithium aluminum hydride, then followed by lithium aluminum hydride, followed by hydronium ion. Okay, if that is the case, so we have solved this. The question now is, how do we form this? How do we form this? Okay, you can go ahead and look at this here. How do we form this? How will you form that? Remember MBS? Remember what we told you about MBS, what it would do? This is an allylic carbon with allylic hydrogen. This is also an allylic carbon with allylic hydrogen. So therefore, excellent. So we use excess of MBS. So excess of MBS will give us that. So if we have CH3, the starting material. Okay, now, okay, let's see. We have CH3, CH, actually this here, we have CH, okay, XXMBS, but if you just do XXMBS, that will give you the 2-bromo, right? Right? That will give you the 2-bromo. Is that correct? If that is correct, say yes or no, or give me a smiling face. This will put a bromine here and a bromine here. Is that correct? Okay, good. If you do that, then the next step is, what is your next step? Step 2? Step 2 will be what? Okay, sodium cyanide. Also, excess sodium cyanide. Okay, so that would displace the 2-bromine. Okay, and then you form the. Now, there's one more thing that we need to do. One more thing that we need to do. Hydrogen, exactly, because this double bond has to go now. Okay, the double bond has to go. So step 3, hydrogen and water, palladium. Okay, that will remove the double bond. Okay, the MBS will place bromine here. Bromine here will replace hydrogen from here, hydrogen from here. The sodium cyanide will replace those 2 bromine here and here, and then the hydrogenation will transform the carbon-carbon double bond into a carbon-carbon single bond, and therefore you form this. Once you form this, then you do lithium-aluminum hydride. Okay, very good. Let's see. There's one problem here. Oh, okay, I want us to do this. What time is it? Okay, 8:22. It's almost 90 minutes. Okay, let's see. Let me see. Who have I not talked to yet? If I have not talked to you yet, can you pick up the mic and just read this for us? I don't think I've listened to Bria. Bria, did I talk to you today?
Draw the structure of the compound. Is that C?
I don't think I heard your voice today.
H2N that exhibits.
C4. Yeah, C4. C4. Yeah, C4. Okay.
C4H7N that exhibits the following HNMR in infrared spectra. Okay.
Okay, very good. Okay, very good. Now, so what we want to do here, begin to now refresh your memory with regard to NMR spectroscopy and also infrared spectroscopy. Now, if you look at this here, look at this signal here at about 2250 wave number. Anytime you look at your infrared spectroscopy and you see a signal in this region, the chances are you have a carbon-carbon triple bond or a carbon-nitrogen triple bond. Those are the 2 functional groups that will give you resonance in this region right here. So what this is telling us is that the chances are we have a nitrile in this molecule. Now, if you also look at this molecule here, you could determine the index of hydrogen deficiency. If you recall, index of hydrogen deficiency from last semester, the formula is number of carbon atoms minus number of hydrogen atom divided by 2 minus number of halogen atom divided by 2 plus number of nitrogen divided by 2 plus 1. If we use this formula here, given the fact that number of carbon is 4, number of hydrogen is 7, number of nitrogen is only 1, the index of hydrogen deficiency will be 2. So what does that tell you? If you have index of hydrogen deficiency of 2, what does that tell you? Anybody has an idea? What does it tell you? Index of hydrogen deficiency index of hydrogen deficiency. Okay, 2 means you have triple bond, 2 rings, 2 double bonds, or 1 ring or double. Excellent. That is what that is telling you. So in this case, they've also told us that we have a triple bond right here, which is either a nitrile or a carbon-carbon double bond. So therefore, this got to the rings is out. So you don't need to worry about rings. Okay. Now let us now look at the rest of the data they've given us. Okay, this is the proton NMR spectrum. This is the proton NMR spectrum, and what do we have here? What does that tell you? This here, the chemical shift is at about 2.3 parts per million. And that is a triplet. This is a triplet. And I will tell you, because of this integration that I see here, this here, and this here, I will say this is 2 hydrogen. Okay, this peak here at 1.7, peak at 1.7 parts per million. They already told us it is a sextet. It's a sextet. And that is 2 hydrogen. And here, the peak at about 1 point, let us call it 1.0. It's close to 1.0. Okay, parts per million. That peak, that is a triplet. And that is 3 hydrogen. Okay, if you look at this here, okay, this is already accounted for all of the 7 hydrogen in this molecule. So what is this NMR data is telling you is that you have 3 types of hydrogen in this molecule. Very, very simple. Okay, if that is the case, let us now construct what is the structure of this molecule. Anybody has an idea what the structure of this molecule will be? What does this tell you? 2.3 parts per million, triplet. What does it tell you? 1.0, let's do this one first. This is easy. 3 hydrogen. What does 3 hydrogen tell you? Triplet. What does it tell you? A methyl group. Excellent. So it tells you you have a methyl group that is next to a CH2. And that is why it is a triplet, because it is being split by, you have the M+1 rule. Remember, M+1, n is the number of hydrogen that is next to it. Okay? Oh, okay. Somebody has given us the answer. CH3, CH2. Okay, Sinead said CH2. Okay, good. Sinead said this must be this. Okay. And then the triple bond. Okay. Okay, Sinead has given us the answer here. Let us see. Is this consistent? Is this consistent with what we have? This carbon-nitrogen triple bond, that is this signal here in the IR spectrum. So that is consistent. Now the 1.3 triplet, that is consistent. This is the 1.0. Okay, where is the 1.7 sextet? Sextet meaning that it is in 5 different hydrogens. Okay, so you have, this must be that. This must be 1.7, because this is seeing these 2 hydrogens here plus these 3 hydrogens here. 5 plus 1 equals to 6, and that is why you have a sextet. And then this one here will be your 2. This will be your 2.3. That will be your 2.3. Let me get this out of the way so we don't confuse ourselves. Which is It's triplet. It's triplet because it is only seeing 2 other hydrogen, and that takes care of everything. So is that clear to all of you? If it is, give me a happy face. Okay, the most important information I want you to take out of here is that the carbon-nitrogen triple bond, you will also always find the infrared signal at about 2250 wave number. If it is clear to you, give me a happy face. If it is not, when you see me tomorrow, you could come and see me. So for those of you who might not have been in my class last semester, if this is not clear to you, come see me tomorrow. Okay, so that it seems to me everybody is happy with this. Okay, great. Okay, let me. Oh, okay, we are almost running out of time. Let's see here. You guys can do this, so we don't need to do that. We did this already. Remember, we did this in class. This is ibuprofen, so we don't need to do this. This is ibuprofen or Advil. So we did that already. So let us see here. Okay. Okay, let's just finish with this and then let's see. Okay, Dylan, go ahead and read this question for us, and then we'll leave for today. Okay, Dylan is okay. There, is your mic working? There, if your mic is working, read this question for us. Probably not working. Okay, Emmanuel, is your mic working? If it is, read this for us. Okay, all of those. Okay, let me go to, I know definitely.
For each of the reaction
Julian,
schemes
go ahead and
depicted
read
below,
this
select the reagent from the table that is to be used at the given step.
Okay, so what we are going to do here, they have given us a whole bunch of reactions. So we are going to do this, and then after we finish this, that will be the end of today's session. Okay, it's a whole bunch of schemes. Okay, let's run through this very quickly. What is A? What is A? What do we need for A? This is a very good review for all of you. What reagent do we need for A? Going from benzene to toluene. What reagent do we need for this? Okay. Okay, with Friedel-Crafts. Okay, Friedel-Crafts. Okay, we need Friedel-Crafts. So that would be methyl chloride with aluminum chloride. And that is your Friedel-Crafts alkylation. Friedel-Crafts, is that right? I might be messing up that name. I don't. Okay, Friedel-Crafts alkylation. Okay, I think it's LE somewhere here. Okay, that's Friedel-Crafts alkylation. What about B? Going from this toluene to p-nitrotoluene. What do we need for that? What do we need? What reagent do we need here? Okay, I'm trying to give you guys some review session. This is mostly from what we did before. Okay, so that would be nitration. Okay, that is what we use to introduce the nitro group to the benzene ring. This is electrophilic aromatic substitution reaction. Okay, now what do you ever see? Going from this here to carboxylic acid. In other words, we now have to oxidize this here. Okay, excellent. So, okay, that is another way of making carboxylic acid. So we use potassium permanganate. Okay, in some acid, dilute acid. Okay, very good. About D, what do we need for D? To go from the nitro to the amine. Nitro to the amine, what do we need? Okay, if you recall, yes, lithium aluminum hydride will do it. Okay. Okay, very good. You could also, or iron in HCl. Okay, so we finished that. Let us go to, okay, this one here. We finish, we do this and then we go home for tonight. Okay, from here to here, what do we do? A. What reagent do we need to go from here? What are we doing here? We are introducing a bromine atom. Okay, what reagent do you need? Okay, bromine, okay, very good. Bromine in iron 3 bromide. Okay, good. Now about B, we now want to make a Grignard. What do we need? Magnesium. Okay, now C, we're going from a Grignard to a primary alcohol. What do we need here? Grignard to a primary alcohol. Step 1. Okay, yeah, you could use formaldehyde. Yeah, we almost forgot about formaldehyde. Yes, do formaldehyde. And then step 2 with hydronium ion. Okay, very good. I was thinking of Grignard with carbon dioxide and then reducing with lithium aluminum hydride. But this is actually better. This one is better. Okay. Now, from the primary alcohol to aldehyde, what do we need? Primary alcohol to aldehyde. PCC, okay. Or Des-Martin, okay, very good. Or Des-Martin, good. Now, from the aldehyde to, what do we need to form here? We want to do chlorination of the benzene ring. What do we need for chlorination? We want to add the chlorine here. Okay, chlorine, very good. Chlorine in ion 3 with ion 3. Alright, so hopefully this is a review for all of you. About F, going from here, we now want to form this cyanohydrin. This is a cyanohydrin. If you remember, reaction of aldehyde or the formation of nitrile. Okay, what do we need here? This is an aldehyde going to cyanohydrin. What do we need? Okay, here, potassium cyanide. Okay, very good. Potassium cyanide. Okay, followed by hydrogen, some kind of hydrogen. Okay. Okay, very good. So we form this. We form the cyanohydrin. Now we want to go from the cyanohydrin to carboxylic acid. G, what do we need here? Carboxylic acid. Okay, what from here to here? Okay, we could do, yeah, we could do hydrolysis of the nitrile. Okay, so that will give us we could go from the nitrile to the carboxylic acid by hydrolyzing in dilute acid. Very good. About here. Now I think we did it before, but I'm sure you guys will not think of it as what we need to do. H. Now we want to go from a carboxylic acid to an acid chloride. This is what you need for that. You need thionic chloride. Remember, thionic chloride would take a carboxylic acid to an acid chloride. Now, what it will also do, also remember thionyl chloride will also take an alcohol to a chloride. If you remember when we did this, thionyl chloride will take an alcohol, a primary alcohol or a secondary alcohol to a chloride. It will also take a carboxylic acid to an acid chloride, which is what you have here. And finally, you want to go to here. All you need to do here, just take the acid chloride and add water to it. That will give you a carboxylic acid. Okay, so that is the end of today's session. Is there any question before we leave? We have, we spent more than 90 minutes already. Is there any question before we leave? Okay, if there is no question, give me a happy face or just give me a green check or any kind of emoticon just to show that you understand what we just did. Is the quiz just on both? It could be on anything. Somebody asked the quiz on 20, it could be on anything. Okay. Okay, folks, enjoy the rest of your evening, and I will see you tomorrow.
Professor Irene?
Yes.
When are you posting the video?
Yes. I will post it very early tomorrow morning. Okay.